This is lecture 41 of condensed matter physics. And in the previous lecture, we have introduced semiconductors and in particular discussed the electron and hole concentration in intrinsic semiconductors. In this lecture, we are going to talk about extrinsic or doped semiconductors and how electron density and hole density in these is calculated. So, today's topic is extrinsic or doped semiconductors. The whole idea of semiconductors is that by doping you can control the number of charge carriers, the conducting carriers of electricity and their type, and that is what makes semiconductors very useful. So, what we have seen and this was done through law of mass action. That in an intrinsic semiconductor, the number of electrons is equal to the number of holes, and this came out to be 2 me star kBT over 2 pi h cross square raised to 3 by 2 e raised to minus E c minus mu over kBT, and the chemical potential mu was equal to E v plus E gap divided by 2 plus 3/4 kBT log of m h star over m e star. Pictorially, what we had then was that here is the conduction band, here is the valence band top, and at temperature T you had electrons out here and holes here, and in intrinsic semiconductor the number is equal, and here is the Fermi level. This is mu or epsilon f, roughly in the middle. Now, by doping we can change this concentration. Now, recall again law of mass action that number of electrons and number of holes irrespective of how they are generated remains the same, and this was equal to 4 m e star m whole star raised to 3 by 2 kBT over 2 pi h cross square raised to 3 e raised to minus E g over kBT, and this is independent of how these carriers, which are electrons and holes, are generated. Now, this is what gives a great control over the kind of carriers you can have, and this is done by doping of intrinsic semiconductors, and I will demonstrate this with the example of silicon. Now, you see silicon has electronic configuration 1s2, 2s2, 2p6, 3s2, 3p4, 4 valence electrons. Compare this with the atoms in adjacent to this in the periodic table. So, let us look at phosphorus. Phosphorus has 15 electrons. So, its configuration is 1s2, 2s2, 2p6, 3s2, 3p5, and on the left is aluminum, which has 13 electrons. So, it has 1s2, 2s2, 2p6, 3s2, 3p3. So, this one is 1 more electron than silicon, and this has 1 less electron than silicon. Now, let us substitute some of the atoms in silicon crystal by, say, phosphorus of aluminum or aluminum. Let us do it one by one. So, let us take phosphorus first. Here are these silicon atoms. I am just making it symbolically, and I put a phosphorus atom here. Substitutional, it is not going into some other site, but it is going into the lattice site. Then this has an extra electron. So, what would happen is that this extra electron is free to move around. And where does it go? Let us look at the band picture. When valence band is full and conduction band is empty, this extra electron has nothing else to go, nowhere else to go, but will go to the conduction band. So, here is this extra electron. The question is, does it move in the conduction band? So, does the extra electron move in the conduction band? And the answer is no. Why does that happen? The electron remains loosely bound to the p plus atom. Now, why would that happen? Because you see, when we had this silicon and a phosphorus in the middle, the electron that came out left a positive charge behind. So, it cannot go very far, it will kind of move around, if you look at the Bohr picture, around this ion, making a hydrogen kind of atom, and therefore, its energy is going to be slightly less than that in the conduction band. So, this implies energy of electron is slightly less than in the conduction band. So, let us make this picture on the next slide. here are these bands. There is this extra electron which would be bound, and therefore, its state would be somewhere here. It is less than the conduction band by E d. So, E d I would call the donor binding energy. If you put many of them, all these states will be here. The doping level is generally 1 in 10 raised to 6. So, these bands, these states do not overlap. So, this implies these bound states do not form a band, but are fixed at energy E d below the conduction band. So, the picture you make is this is E c, and here are these donor levels. Donor because it's donating an electron, and here is E c. Now, what you can see is that most of these electrons would go to the conduction band at some temperature, because this energy we will calculate is very small, and they will dominate the electrons coming from the valence band. Let us just quickly do an order of magnitude estimate. So, I said that doping is of the level of 1 in 10 raised to 6. So, let us say there are 10 raised to 17 per centimeter cubed donors, and they will give roughly 10 raised to 17 per centimeter cubed electrons in the conduction band. Whereas, what we had seen earlier is that the number of electrons in an intrinsic semiconductor is of the order of 10 raised to 10. So, orders of magnitude higher electrons are given by donor levels, and therefore, I can just ignore any electrons coming from the valence band. This is valence, and all the electrons are coming from donor level. This is also will make sense when you do the energetics. So, first job now is to calculate the donor level energy. So, let me make now this conduction band like this, and here is the donor level. We want to calculate this. So, number 1, kinetic energy of electron is h cross square k square over 2 m star in the conduction band. So, when it is moving in this conduction band. So, that means, in calculating hydrogen like energy for this electron bound to p plus ion, we should use m e star instead of free electron mass m e. So, that is one change that is going to take place. The other thing I want to point out is that the radius of electron would come out to be much larger than Bohr radius. And that means, this implies that electron orbit encloses many atoms, and therefore, effect of these atoms can be taken care of by dielectric constant of silicon. And let me point out that this is a self consistent argument. In that large epsilon dielectric constant gives large radius, and this implies epsilon can be used. So, it is consistent with each other, and therefore, I can do that. So, let us quickly now estimate the energy. Now, E hydrogen is equal to minus 13.6 eV, and recall that E hydrogen is proportional to mass of the electron and e raised to 4. So, now we replace m e by m e star and E square by E square by epsilon, where epsilon is the dielectric constant. And therefore, E donor magnitude is going to be equal to the energy of the hydrogen atom, and I divide this by m e and multiply by m e star and divide by epsilon square. That is going to be the donor energy. So, I can write that the compared to E c, the energy is lowered by this much magnitude, which is mod E d equals 13.6 times m e star by m e times 1 over epsilon square. Let us just quickly do a calculation, estimate. Epsilon is of the order of 10 to 100. So, let us take it 10. m e star over m e of the order of 0.1. Then you see that mod E d is of the order of m e v. Therefore, if I make this picture again, this is E c, this is E v, roughly 1 E v difference, whereas the donor level out here is m e v level difference. If you compare e raised to minus m e v by k b t, it is much greater than e raised to minus e v by k b t. So, you can see from this argument also that the number of electrons that will be given by the donor levels will be much larger, right, up to e raised to whatever power 1000, e raised to minus eV by kT raised to 1000, larger than the electrons coming from the valence band. So, all the electrons in the conduction band in this kind of system can be taken to be coming from the doped atoms. Now, this is a quick calculation of the donor level. Now, same thing would happen to the acceptor level. Now, this is where the concept of hole comes in really handy. Acceptor level. What is happening in the acceptor level is this, that you have these silicon atoms, and in between I have put this aluminum atom. This is one less electron, and therefore, one electron can come from some other system, some nearby atoms, creating a deficit on those atoms, and this deficit is the hole. We want to calculate how much energy would it require for this to take place, or how much is the binding of the hole. Now, if you look at the picture in the band form, here is E V, here is E C, and I will show you that just like there was some energy required to form, to take the electron, make the electron free in the case of donors, here also to create a hole one would require certain energy. So, the level is going to be somewhere here, which I am going to call E acceptor, and we will do that calculation in a bit. So, what is happening is that the electron from here need to be promoted to this level in order to create a hole. If the energy level difference is very small at room temperature, there will be a lot of holes created. So, what will happen finally is that there will be a lot of these electrons sitting here, and you will be creating the holes out here. The energy required out here, this difference I am going to call E A, the difference. Now, if you look at the corresponding picture in terms of holes, what is happening is this. Here is the conduction band, here is the valence band, this is E V. If I make the corresponding hole picture, so I will forget about the conduction band, this gives me the hole band, and this is minus E V. Recall that epsilon hole equals minus epsilon electron. So, in the whole picture, I have this energy, and I will be creating E acceptor at this level. And this has lots of holes because there is one electron missing, and they would require some energy E A to get promoted to the hole band. This is exactly the same picture as for donor levels or electrons, except that everything else is being calculated for a hole. I have just inverted the missing electron band and made it a hole band. Now, the picture looks exactly the same. So, what we see is that there is a electron band and here is the level below this, a donor level, and there will be this hole band, and below this will be by energy E acceptor, the acceptor level. This one is populated by electrons, this one is populated by holes. It requires energy E d to move up into the conduction band. It requires energy E a for the holes to move up to the hole band or create that hole in the valence band. Now, energy E a is calculated in exactly the same manner as E d. The picture we have is that here I have the negative aluminum ion Al minus, and there is a hole moving around it. So, this is also like hydrogen atom with positive and negative charges switched. And the mass of hole is going to be mh star. So, E a magnitude is going to be equal to 13.6 mh star over me times 1 over epsilon square. And again you will see that this will be of the order of MEV. So, I have this picture where I can take an intrinsic semiconductor, dope it with donor atoms, or I have this intrinsic semiconductor and dope it with acceptor atoms. What will happen here is that you will have lots of electrons here, and by law of mass action, number of holes will go down in the valence band. In the case of acceptor, you will have many holes here, but the number of electrons will go down. Why? Because N p is constant. So, you have created two different types of semiconductors, where the carrier charges are different, their Hall coefficient is going to have different signs, and you can also control the number of charge carriers by appropriate amount of doping. This is known as N type semiconductor, and this is known as P type. Semiconductor. So, what we have learned so far is how to calculate the energy levels, and by calculating we have also seen that the charge carriers electrons in N type semiconductor and holes in P type semiconductor will be given mainly by either the donor atoms or the acceptor atoms, and the other charge carriers become really small in numbers. They do not really matter much. So, we found this control to be done over this material. Let us now, since we have done the energetics, calculate what will be the number of electrons, and the same calculation will go for number of holes for acceptor atoms. Number of electrons in the conduction band in an n-type semiconductor. And let me note, similar calculation can be performed for calculating number of holes in the valence band of a p-type semiconductor. So, to do this calculation, let me make this picture again, where I have E c, E v, and here are the donor levels. And the probability of occupation is something like this. We draw a picture here, line, this is the number of electrons, and here, since the occupation is not complete, so number of unoccupied atoms is less than N d, where N d is the number of donor atoms, and all those electrons would have gone to the conduction band. So, let us give some nomenclature here. N d is equal to number of donor atoms per unit volume. The energy E c is the energy of conduction band. E c minus E d is the energy of donor levels, and as I pointed out earlier, that electrons in the conduction band can be taken to be equal to the electrons coming from the donor atoms, because that is 6-7 orders of magnitude larger than those coming from the valence band. So, that the others can be ignored. So, we have seen that number of electrons in the conduction band is equal to, if you do whatever calculation we did earlier in the previous lecture, is equal to 2 m e star k b t over 2 pi h cross square raised to 3 by 2 e raised to minus E c minus mu over k b t. And I just want to point out here that assume E c is far from mu, which in this case would not be strictly true, but nonetheless we can do an approximate calculation. So, let me just keep making that picture again and again, E v, E c, and here is the donor levels. I am showing them by dotted line because it is not a band. the different levels. So, I have n equals 2 m e star k b t over 2 pi h cross square raised to 3 by 2 e raised to minus E c minus mu over k b t, which I am going to write as n 0 e raised to minus E c minus mu over k b t. Here n 0 is equal to 2 m e star k b t over 2 pi h cross square raised to 3 by 2. And this number is the same as the number of electrons that have come from the donor level. Now, occupation probability at the donor level, F at donor level is equal to 1 over e raised to E c minus E d, that is the energy level of the donor, minus mu over k b t plus 1. This is the occupancy probability. So, the number of donor atoms with electron in them is equal to n d divided by e raised to E c minus E d minus mu over k b t plus 1. And this means number of atoms that have given their electron to the conduction band is equal to n d minus n d over e raised to E c minus E d minus mu over k b t plus 1. And again making the usual approximation, I take E c minus E d minus mu over k b t to be much greater than 1. Now, the approximation we made earlier, this is going to be equal to n d e raised to E c minus E d minus mu over k b t divided by 1 plus E c minus E d minus mu over k b t. This should have been, so this is not correct, this is the other way. This is not the approximation we were making earlier, this is the approximation we were making. E raised to this, that is the correct approximation. So, this therefore can be written as this part can be ignored and you can just write n times the exponential function. So, let me do it again. We have number of empty atoms is equal to n d 1 minus 1 over e raised to E c minus E d minus mu over k b t plus 1, and under the approximation that e raised to E c minus E d minus mu over k b t is much less than 1, this goes to N d e raised to E c minus E d minus mu over k b t. And all these electrons have gone to the conduction band. And therefore, n square is going to be equal to 2 m e star k b t over 2 pi h cross square raised to 3 by 2 e raised to minus E c minus mu over k b t times N d e raised to E c minus E d minus mu over k b t. It is exactly the same calculation that we had done earlier in case of intrinsic semiconductors, and this can be written as N 0, where N 0 is that 2 times the factor and all that, N d e raised to minus E d over k b t. And therefore, the number of electrons in the conduction band is N 0 N d raised to 1 half e raised to minus E d over 2 k b t. This is roughly the case. And similarly, if you do a similar calculation, for p type semiconductors, you will find that p equals N 0. N 0 will come with m h star now. So, let me write N 0 whole n acceptor raised to 3 by raised to 1 half e raised to minus E a over 2 k b t. I want you to derive this formula. So, we have calculated what the number of electrons, the number of holes would be, what are known as majority carriers in the donor or the n type or the p type semiconductors. Next question you can ask is, what about the number of holes in an n type semiconductor? So, for this use N p equals N 0 N h N 0 h e raised to minus E c minus E v over k b t. We have already calculated n or p, and you can calculate the other number. So, I will just stop here on this. I want to give you a question here. What is the position of the Fermi level in a doped semiconductor for both n type and p type? Is it at the donor level, at the acceptor level, somewhere in between, or at half the band gap. Please explore this. And in light of this, also see if the approximations that we made in calculating the number of electrons and holes are justified, or is this a much more approximate calculation than it was for an intrinsic semiconductor. So, this is how you do the calculations for the N type and P type semiconductors. The next question I want to address and do a comparison is for the conductivity. Of now, recall from Rude model or free electron model that the conductivity sigma was given as n E square tau over m. In the present case, we will talk about this in terms of mobility. So, this can also be written as n mobility times E, where mu is E tau over m and is known as mobility of the charge carriers. Let us quickly recall the numbers for metallic systems. Mu is n, no, not n, E tau over m. Now, for metallic systems, we had the resistivity of the order of 10 raised to minus 6 ohm centimeter, and therefore, conductivity of the order of 10 raised to 6 ohm centimeter inverse. Now, for semiconductors, resistivity for intrinsic semiconductors is of the order of 10 raised to 2 ohm centimeter, and conductivity is of the order of therefore 10 raised to minus 2 ohm centimeter inverse. And for doped semiconductors, n goes up by a factor of roughly 6. So, rho will be of the order of 10 raised to minus 4 and sigma will be of the order of 10 raised to 4 ohm centimeter inverse. Now, these are best described in semiconductors in terms of mobilities. So, mobilities of carriers in semiconductors. So, mu is of the order of 1000 centimeter square volt per second for semiconductors. Let me give you this question, compare with mobilities of electron in a metal. You will see that in metals is roughly smaller by a factor of 10. But let me give you some mobilities for some systems. So, mu electron, mu hole, and system I am going to consider are diamond, silicon, germanium, indium antimonide, indium arsenide, and indium phosphide. Mu electron, and this is all in centimeter square per volt second. Mu electron for diamond is 1800, mu hole is 1200, silicon is 1350 and is 480 for hole. For germanium is 3600, hole is 1800. For indium antimonide is 800 for electron and 450 for hole. For arsenide, indium arsenide is 30,000 for electron and 450 for hole, and indium phosphide is 4500 for electron and 100 for hole. Notice that mu hole is much less than mu electron in some cases, and generally less than mu electron. This is taken from Kittel's book. So, you see this is of the order of 1000, 2000 and can go as high as 30,000 for indium and antimonide, and compared to metals, the mobility of electrons and holes, electrons in semiconductors is much larger. Holes are slightly smaller because generally it is seen that hole bands overlap, and therefore, instead of moving in a band, they make a transition to the other band. So, this is the kind of numbers that you have in these systems. The difference in the mobility also gives a Hall conductivity which is not 0, even if the number of electrons and number of holes are the same. We have done a problem on this in the past, and maybe I will repeat this problem again. We will do it again in the context of semiconductors. So, with this, let me conclude my lecture on extrinsic semiconductors. We have calculated energy levels of donor and acceptor atoms under some approximations number of electrons and holes in N and P type semiconductors have been calculated, and 3, mobilities of electron and holes have been discussed. It is usually seen that mu h is less than mu p, and this affects the transport properties of or conductivity and other transport properties of these systems. Thank you.